one of the things you'll be required to do in this lab is create test grids. So I have made some test grids. They're a bit smaller than the ones we'll be doing in the lab. These are 2 by 2 instead of the 3 by 4s that you'll be doing in the lab. But the concept's the same. And so you want one test grid that's going to be for your predictions and another one that's for actual. So your predictions you're going to guess using the solubility rules. And the actual is going to be what you measure in the lab, what you record in the lab. And so again, you're going to want to make both these test grids, the predictions will be created before you get to lab, and the actual test grid you'll be filling that in and populating it with data in the lab. So again, draw both these before you get to lab. Now, so let's take a look at some mock data here. So if we use our solubility rules, lead with chloride should produce a precipitate that should be insoluble. So this one would form a precipitate according to the solubility rules. Hydroxides are insoluble with most metals, so lead hydroxide should be insoluble, meaning we should make a precipitate. Copper and chloride should be soluble, so we should see no precipitate in the reaction of the copper nitrate with the sodium chloride. And of course, all sodium compounds and all nitrates are soluble. And then finally, copper and hydroxide. Hydroxides are generally insoluble, and so we should see a precipitate form there. So our predictions are that 3 out of 4 of these compounds should produce precipitates based upon the solubility rules. Now be aware that our predictions may not match exactly our actual data. The solubility rules are guidelines, and sometimes they don't work perfectly, and we'll talk more about that in a few moments here. But right here we have our actual data. So the lead and the chloride do form a precipitate as predicted. So check, that looks good. If we combine the lead with the hydroxide, again we form a precipitate. So check, that looks good. This one again matches our predictions, but here we have a contradiction. So here we have a combination of ions, the copper and the hydroxides, that should produce the precipitate according to the solubility rules, yet it does not. So one of the things you'll be asked to do in the lab is to explain contradictions. So there's a number of things that can cause you not to form a precipitate during the combination of ions that are predicted by the solubility rules to make precipitate. So things that affect solubility are going to be, maybe our concentration's too low, maybe our temperature is too high, maybe our ratios aren't right on. So, you want to explain, maybe what might have caused this to occur. Maybe that combination of ions is slightly soluble, and we just didn't have enough of it in solution to form precipitate. Or maybe it's slightly soluble and the temperature was a little too high, or maybe the reaction's slow. It could be a number of things. So you want to try and do your best to explain what could have caused any contradictions. And if you're lucky, you'll see no contradictions, and hey, that'll save you some work, right? That'd be great. So moving on to talking about part B, one of the things that's going to be very important here is going to be how you smell the chemicals. So if I remember correctly, part of the procedure calls for you to identify what sort of smells are coming off the container. And so you want to avoid sticking your nose into the flask. So if you stick your nose into the flask or near the flask, that can be very dangerous. That can actually injure you or poison you or burn you, so don't do that. So what's the proper way to smell a reaction that may be producing some kind of dangerous vapors? You want to hold it pretty far from your nose and use your hand to gently waft the smell up to your nose. So again, waft, you're going to wave your hand. And if you look at the picture here, you can kind of see the blurs here. I'll draw him some motion lines here, like a comic book, and you see his hand is moving in the picture, and he's just gently sort of blowing and moving and paddling those vapors up close to his nose until he gets the smell. So again, don't stick your nose close to those reactions. Some of the vapors in the reactions in part B can be pretty unpleasant, maybe even poisonous in high concentration. So just be very gentle in terms of wafting them towards your face, and then you'll be just fine. All right, on to part C. Now part C is the most challenging part of the lab. You'll be given a series of unknowns, and you're going to have to combine them together in order to figure out which one's which. And you may also actually have to expand and combine them with stuff from part A or part B. And if you want to do those other combinations, then just ask the instructor And the structure will give you clearance about whether or not it's safe and how to handle the waste and stuff. But if you're lucky, you might be able to figure them all out based upon just mixing them with each other. So for this particular example, it's a little bit smaller than the one you'll be doing lab. I've only chosen 4 unknowns. So we have sodium carbonate, sulfuric acid, potassium chloride, and copper 2 nitrate. But we don't know which one's which. So they're labeled A through D, but we don't know which one's A, which one's D, and etc., etc. So how do we figure it out? Well, we're going to mix these things together and see what happens. And so we're going to want to systematically mix them together. So we're going to combine A with B, A with C, and A with D. There's no need to combine A with A because A is the same thing. So don't combine A and A. Combine A and B, A and C, and A and D. And so that's A with every possible combination. Now from there we can combine B and C, B and D, and we don't need to combine A and B because we actually already ran that test earlier. And then finally, the last combination that we haven't tried yet is C and D. So we're going to have more unknowns. It's going to be more combinations you'll be trying. So make sure you get every one of those combinations. And notice we have avoided any duplicates. Like for instance, we don't mix D with C because we've already mixed C with D, and that'd be the same thing. And we don't need to mix like A with B again because we tested that earlier. So test all combinations and avoid duplicates, and then record your data. So our first one gives no reaction, so a lot of the combinations might not do anything. But this one right here is unique because it gives us formation of a gas. That's going to be important for identifying these things. A and D, no reaction. B and C, we have a precipitate. B and D, no reaction. C and D, no reaction. So what does this mean? Well, we can figure out which one's which based upon the stuff we did in parts A and part B. So for A, from the results on the previous page, we can conclude that that's H2SO4, or sulfuric acid. And you want to explain your justification. Now, if you say something like, oh, it matches the rules, well, that's not going to get you any credit. That's not enough detail. You need to explain your logic. You need to support your answer with data. And I've given some examples right here. So A and C, if we go back to the previous page, that formed a gas. Now there's only one combination that should form a gas, and that's going to be an acid with something with carbonate ions. So the acid and the carbonate should form CO2. We should see bubbling. So that means that A must be either sodium carbonate or sulfuric acid, given the fact that this reaction produced a gas. Now, how do we know which one's which? Well, what we see is A did not form a precipitate in any of the reactions, but the carbonate ion would. So let's say that A was, if A happened to contain a carbonate ion, then that would have formed a precipitate when we reacted it with something else. And so you can see A formed no precipitates. So A can't contain a carbonate ions, therefore A must be sulfuric acid. Now this stuff's tricky to think through, so it's going to take some work on your part. And you know, if you're having a little trouble following, you have to think about it some and work your way through it logically. But you want to, you know, again, apply data, apply logic. On to copper nitrate. So B is identified as copper nitrate from our results, and the way we can tell is that B and C formed a precipitate. Now we already concluded that you know, A and C made a gas, and we realized that A had to be sulfuric acid. Therefore, C must be carbonate. It must have carbonate in it. And so that means that B has to be copper carbonate. So B and C form a precipitate, and our solubility rules predict the only precipitate we'd form would be copper carbonate. And therefore, A and B, because A and B did not form a gas, then A cannot, or excuse me, that B cannot contain a carbonate, so B has to be copper nitrate. So copper nitrate plus our sodium carbonate gives us a precipitate, and those are the identities of B and C. So B is a copper nitrate, and C is sodium carbonate. This stuff's tricky. You're gonna have to, it's gonna be hard for you guys, but you're just gonna have to work through and clearly explain how you apply your rules and how you apply your logic. So we already figured out, because A and C produce a gas, means that A has, excuse me, I guess that should be a C right there, so let's fix that. So that means that C must either be sodium carbonate or sulfuric acid. And because B and C form precipitate, that means that C has to be sodium carbonate, because our solubility rules predict that carbonate should form a precipitate. And then finally, KCl. KCl gave no reaction with any compound. And again, according to our rules about what's going to form a gas and what's going to form precipitate, the only thing that should form no reaction with anything should be potassium chloride, and that should be D. And we can also sort of arrive there based upon process of elimination. So that's it, gang. Good luck on the pre-lab, and good luck in lab.